Hello and welcome to this talk here at Develop 2020. I'm Dr. Tommy Thompson from AI in Games, and in this talk I'm going to be talking about artificial intelligence and video games. Shock surprise, what it is, how it works, and perhaps more critically, how it is evolving within the video games industry. So this means we're going to take a moment to discuss how AI has historically been used in games, the tools and techniques that have achieved the most prominence, as well as some novel applications, but also looking more critically at the future of the medium and the rise of machine learning, notably deep learning, and how this is beginning to change how AI is adapted and adopted within our games, not just influencing the types of games we're creating, but also how we're making them as well. So a little bit about AI in Games and me specifically. AI in Games has operated since 2017 as a company to support studios big and small in understanding how AI technology in the context of video games can work. And this revolves around three key pillars. First of all, research consultancy, identifying opportunities and potential technologies for building new tools and features within our games, working as part of a development team, either on a hands-on basis as a programmer or a more periodic basis as a design consultant. And then also in communication, working with a studio to help better share and promote the work that they're doing both to their customers and stakeholders. And in the past couple of years, we've worked with a variety of companies, big and small. And myself personally, in between working at AI in Games, I am also a lecturer in informatics at King's College in London, teaching classes on artificial intelligence. However, for some of you, the name of the company and even my voice may seem rather familiar. AI in Games started as a YouTube channel that explores research and applications of artificial intelligence in video games, and has since grown into a modestly successful channel with millions of views behind it. I mean, it's safe to say that being a YouTuber was not a career aspiration I had in my 30s, but hey, it is what it is. So let's go back to the very beginning. What are we talking about when we say artificial intelligence? What do we actually mean? The reason I bring this up now is that quite often AI is a term thrown around to obfuscate any sort of computational process, included for marketing purposes, given it just makes it sound really, really smart. And so if we were to actually take the more academic notion of what we are talking about when we say artificial intelligence, is that we're looking at a software system, often known as an agent, that will make intelligent decisions. This will be a system that is intended to be autonomous, so it can make those decisions on its own accord, and it doesn't have to worry about human input, but also that it is rational. It will always make the best decision it possibly can, which is where 99% of science fiction comes from, because we always assume that the best decision isn't always the most humane one. And so it's worth acknowledging at this time that machine learning in particular and AI are actually kind of distinct from one another. Although in the media, usually when you're hearing about AI these days, what you're actually hearing about is machine learning, or actually deep learning, which we'll get to in a second. What separates this is actually quite important in terms of the programming, design and usage, and also how and where they can work in games, which we'll talk about later. Classical AI is systems where there is an understanding of the problem. We actually encode the problem space into a state space where we can then have actions that allow us to then, as a programmer or designer, search that space to find good solutions to that problem. Whereas machine learning, this is actually a subset of artificial intelligence where what we're doing is building a data processing model or a function that interprets this incoming data and then generates some useful output for us. And ultimately, we refer to the process where we're training them such that they're actually getting better at solving this problem through continued iteration as learning. But really, if there's one thing to take away at this point, is that I always like to say that AI pretends to think like it's a human, whereas machine learning pretends to learn like it's a human, even though AI doesn't learn. When we say that a machine learning system has learned to solve a problem, what we're really saying is it's learned how to maximize a particular function by generalizing over a very large set of data. And we're going to come back and talk a little bit more about that, as well as deep learning and what that means in this context later in this talk. So let's get into the meat of this. I wanted to start my talk by really discussing how artificial intelligence has historically been used in video games and what techniques have achieved prominence across the industry. Now, one of the key things to acknowledge in this situation is how different AI typically is in the context of video games. When we think about artificial intelligence outside of video games, we're typically thinking about optimality, of systems that make intelligent decisions and find optimal solutions to complex problem spaces. This can range from rovers that we're sending off to Mars, or self-driving cars, voice recognition, and even things like robotics. However, when we think about it in the context of games, it's typically in a very different format. I often like to think of AI in games as a mechanism that supports a performance art, supporting game worlds and environments to give them a sense of realism. And this often results in making interesting decisions that don't necessarily have an optimal answer, given we're trying to create fun. And so, of course, fun is a highly subjective concept. In addition, games are meant as a framework through which to reward players for successful behaviour. And this often means we need AI to be fallible. Otherwise, it's not going to be a fun experience if players are overwhelmed by ruthless AI characters. Well, in theory, because players can be kinda masochistic sometimes. But adding to this issue is that game development is of course a complex multidisciplinary process. AI programmers are seldom the only person in control of the gameplay experience. They will be liaising with other programmers, as well as designers, animators, sound designers, and more, on how these systems not only work, but also are successfully communicated to the player. Hence, there is a need to build tools that support designers to playtest and investigate intended and undesirable behaviour, to remove complexity or enhance it as players give feedback. Unless, of course, you're a small indie band, which means, of course, you don't have time to build super complex AI, given you're doing everything else I already mentioned and more as part of development on your game. But the big takeaway here is that AI developers in games are often a unique breed. They have some very specific understanding of game challenges and quite often have a stronger grasp of more classical AI theory, but it's seldom applied given the unique nature of games. Why is this? Well, if I were to ask you, the viewing audience, what's the primary gameplay function of using AI in a video game? The answer's pretty obvious. That's right, building better bad guys. We need something to beat up, or kill, or just outright defeat in a less violent context, or at a push we need other non-player characters that players can interact with. And what is quite interesting is that while there is a fairly broad set of methods that have emerged for game AI, not only are they largely exclusive to the industry, in the sense that these techniques aren't really used outside of video games, but also there is little consensus on some of the larger challenges that face game development, and we'll come back to that in a minute. So let's quickly walk through some common examples and where they emerged from. First up, let's take a look at finite state machines, largely popularised by Valve in Half-Life back in 1998. Finite state machines are arguably the most vanilla and simplest notion of AI in a video game. It's a simple model of cause and effect, whereby we have some state in the world, and then based on an event that happens in this world, the state, which is actually a particular behavior, such as maybe patrolling a region, guarding a location, or attacking a player, is going to transition into another behavior. And these are things that are quite easy to model and quickly encapsulate and create relatively fast, flexible behaviors very quickly. And this is actually still used quite prominently throughout video games. Some of the biggest examples I can think of off the top of my head are, of course, the Batman Arkham series. And in fact, the likes of Doom, the 2016 reboot, and Doom Eternal are built upon this framework. One of the problems with it, of course, is that it doesn't scale that well as more states are introduced and becomes increasingly complex. Next up, we have arguably the most popular and common format, which is behavior trees, which essentially is taking the decision selection process and turns it into a directed graph of a top-down structure. This is actually the most popular thing because it's also built into Unreal Engine. This is the primary AI methodology built into Unreal Engine 4, and it allows for a lot of integration between programmers and designers, and was largely popularized courtesy of its implementation in Halo 2. The other big AI innovation in the early 2000s is, of course, goal-oriented action planning, or GOAP, which was used in 2005's first encounter Assault Recon by Monolith. This is actually derived from the Stanford Research Institute Problem Solver, which is an AI planning system that dates back to the early 1970s, where we actually model actions as a series of preconditions and effects. And this allows for really simple but intelligent combinations of actions one after another, which are then pumped into a finite state machine you can see in the bottom corner. It's not great for long-term decision making. It doesn't really scale up to larger, more complex solutions, but it's great for very quick reactive behaviour, to a point that fear is still held in very high regard to this day. It's Director AI, which is systems that manipulate and change the game world to keep the excitement focused on the player. This has been popularised by Left 4 Dead and is used in a variety of open world AAA games, with another well-known example, of course, being Alien Isolation, a game that I have discussed at great length over on the YouTube channel. But then, in conjunction with the likes of goal-oriented action planning, we also have hierarchical task network planning, which was actually originally put into Killzone 2 by Guerrilla Games, but has subsequently been used in a variety of titles. A very good example of this actually being Horizon Zero Dawn, also by Guerrilla. It is essentially the same principle as goal-oriented action planning. We have actions with preconditions and effects, but this time we essentially have macros of actions which can then be put together into hierarchical structures, which ultimately results in a system that behaves markedly like behaviour trees, which is why it's becoming increasingly more popular and prominent. But one of the big issues that impacts everyone, from the biggest of AAA studios to the smallest of indie devs, is that, as you can see, there's a variety of different tools and there's no consistency. And there's even more tools I didn't talk about in this opening segment of the talk. We have utility AI, constraint satisfaction programming, influence mapping, and many variations on pathfinding algorithms. The big problem here is that, unlike many other problem spaces such as physics or graphics, there is no real consensus on what are the best tools to use. And that's because each methodology caters to different types of problems and different games. There's no definitive solution to the AI problem in video games. And this is exacerbated by the lack of consistency in engines as well. If you look at the bigger players, be it Unity, Unreal, and even CryEngine or Lumberyard, the only consistency is navigation meshes, which is the tool to move characters around on planes and surfaces. Unreal has arguably one of the best behaviour tree tools that you can use out the box, while Unity is a mishmash of interesting opportunities right now, none of which fleshed out sufficiently that would actually enable a developer to really use it with any consistency. And this also means that ultimately AAAs are reinventing the wheel with each engine, or even different versions of the same engine across different studios, just so they can have these AI features. And it's not just reinventing the wheel, there are so many issues that are pervasive across games where we simply don't know what the right answer is. And in some regards, this is good. It's a sign of innovation and growth in game design. But just to list some ideas off the top of my head, you have issues of navigating in the air, for games like Horizon Zero Dawn, or navigating in water for Sea of Thieves. You have crowds of AI characters seen in games such as Hitman and Assassin's Creed, and complex multi-agent environments like the upcoming Watch Dogs Legion. These aren't just interesting design problems, they're fundamental technology problems, and it requires bespoke solutions that will arguably not scale or adapt to different problem spaces. Ultimately, we're not just having to invent new wheels with each project, but also reinvent existing ones. And you'll note that I haven't even mentioned anything that involves machine learning, and there was some interest and enthusiasm in machine learning for games that petered out in the early 2000s. Games such as Total War, Black and White, and Creatures all used neural networks in order to try and achieve different facets of their games, but one of the reasons that it never really took off at that period was that it was a little unreliable and inconsistent, and there was a lack of accessibility built around these tools such that it could be designer friendly. And as a result, it kind of petered out, but it is now coming back in a very big way. And so with machine learning on our minds, let's turn to it now. Everything we've seen so far is about building systems with rules and constraints on what the system is expected to do based on the signals it's receiving. What machine learning does is really quite different, and if we take a moment to briefly discuss how it works, and particularly with deep learning as well, we can see new opportunities in how AI can be applied within games. Now, please bear with me, this is a massive trivialization of this entire field, but hopefully you get the gist of it. Ultimately, with machine learning, we're attempting to train a data structure to store information about a situation or problem, where, after training it, if we give it information about a problem, it can then provide answers very quickly. But of course, this requires us to train it properly. Training requires time and data. Once you have training data for it to compare against, you can improve the data model. Other times you give it the data and the function to optimize against it, and then you leave it to figure it out itself. And a very common approach for this is the use of a neural network, which is what you can see on screen now, where data is fed in and then the desired output comes out. But in order for this to work, we have to train this network, and that involves not only changing the topology, but all of the connections between these layers that you can see, these are actually weighted. And then essentially this creates a massive weighted summation function. So if we can then customize the weight values, we can get different behaviors. But also, what's kind of important here is that when training, the data needs to be filtered correctly. Information needs to be extracted in such a way that it's going to help the learning process. And this is where deep learning actually comes into this. Deep learning is a subset of machine learning that is focused specifically on neural network applications with a training mechanism known as reinforcement learning. One of the things that's really great about deep learning is that we actually have specific features in the network design that allows for particular activation functions, but also more critically feature extraction. Without much need for human oversight and input into the training process, networks are built to capture the interesting features of a problem as part of the learning process, rather than a human having to go in and do it all for you in advance. Ultimately, deep learning systems, once trained, become very good in areas such as pattern recognition, object identification, natural language processing, and other really complex, multifaceted decision-making processes, where writing really simple rules to encapsulate that behavior just really isn't sufficient. And it's what really separates it from the more traditional methods we've already described. And more recently, much of the sensation around deep learning in games has been how it was employed to create grandmaster players in games such as Dota 2 and also in StarCraft 2. But these particular processes are not only just indicative of the great opportunities of deep learning, but also some of the challenges faced in making this a reality for pretty much any studio of any size. And a lot of it is down to tools and money. With regards to tools, however, there is actually a suite of open source software that is being updated and provides really useful means to train and develop deep learning applications for games. However, it's important to acknowledge that all of this will actually require significant compute power and resource to train. We'll get to that in a second. But as you can see, there's a variety of different tools that are available, not just for deploying and training your deep learning systems, but also you have a variety of libraries that will help you solve specific problems and tasks. OpenCV, for example, is a great one for things such as object recognition. But ultimately, coming back to the critical part, we still need to train the systems we're going to use. Training is the most time-consuming process of machine learning and deep learning. But with the trade-off that once it's trained, the inferencing, or runtime execution, is incredibly fast. I'd argue that you will probably spend 90% of your work in preparing, designing, developing, and then training your actual neural nets, and then actually hooking that into the final ecosystem at the end is actually the most cheaper part of the process. But ultimately, as you can see here, this requires a huge amount of compute resource, be it using something like Google's tensor processing, Amazon's cloud services, Microsoft Azure, or your own smaller deployed setup. Depending on the scale of the problem, more processing power is required, and this can be expensive. And this is certainly where the allure of things like Google DeepMind's AlphaStar is quite misleading, given that those StarCraft bots cost tens of millions of dollars to train and actually reach a point where they were surpassing all human behavior. And this is arguably the main reason why deep learning, not necessarily machine learning, could be in some cases outside of the grasp of smaller independent studios, as this requires a lot of experimentation, a lot of research, and a lot of compute resource in order to make it happen. And we're actually seeing a lot of work that is emerging as AAA publishers, notably Electronic Arts and Ubisoft, have developed entire deep learning R&D centers built around mitigating these costs over time by finding great technologies that they can then utilize in future products.
And if you're interested in finding out more about machine learning and really getting to grips with how it works, I'd strongly encourage that you check out Andrew Webb's presentation, which is going to be later on this week at Develop. It sounds like an ideal avenue for people who are new to this space to begin to get to grips with it, and I think it'll be a really great talk to check out.
So let's wrap up by talking about how this changes where we can apply AI in games and look at some of the really interesting examples over the last 10 years of where both machine learning and then deep learning specifically is being used in the video game industry. Arguably, the most successful application of machine learning in recent years is player modeling and being able to encapsulate and capture player data, potentially with the ability to then reproduce it. And this has been deployed in a number of different games, but arguably the most well-known example is Drivatar, which has been in every entry of the Forza series since Forza Motorsport 5 back in 2013, up to the most recent entry, Forza Horizon 4. Drivatar relies on a principle known as Bayesian learning, where the system is gathering data from the player's racing performance in every race and training a neural network to reproduce the player's performance at specific points during future races. The system is generalized such that it isn't race, track, or vehicle specific, but it does try to adapt the performance based on in-game conditions. Ultimately, what it wants is to calculate the expected utility of the vehicle, regardless of whether the player has ever actually been in that vehicle or on a track that they've maybe never even raced before. But the critical part is that this doesn't happen on the player's console. It's all happening on the Azure cloud, given the training process is not something we want to happen on the user's device. We actually deploy it all up to the server, and then the game actually downloads new Drivatars before it begins another race. Drivatar has been, up until recently, one of but a few examples of modern machine learning for character control, but it was an innovation prior to the current deep learning boom. Meanwhile, MotoGP 2019 is one of the first commercial titles to use deep neural networks for a computer-controlled character. One of the reasons this works really well in MotoGP is due to the nature of the game. Racing is a real-time continuous control problem, but it also has very specific constraints brought on by the nature of the game itself, but also the physics of the racing environment. And while this does require a lot of specific optimizations and tweaks, the neural network player used in MotoGP, codenamed Anna, is one of the first major deep neural network applications in games and successfully achieves the desired development outcomes. Another major innovation is actually in animation, or more critically, creating animation controllers for characters in games. As any animator will tell you, building an effective animation is fine, but building a controller that will actually ensure that there are smooth transitions between animations, as well as preventing issues such as foot sliding, is an incredibly complicated and difficult problem, especially as characters are used in a variety of different environments and situations. And so one of the tricks is to use a machine learning system to learn the best points for specific animation transitions. Once trained, the controller can work in-engine as normal. This significantly reduces the labour-intensive process for animators or programmers to find these transition points by hand. There's no clearly defined procedure for doing this, but the research in this space is evolving rapidly, dating back to some inaugural work in the Hitman series that employed a motion matching technology as early as Hitman Absolution, and then of course the 2016 reboot. This same technology was then embraced by Ubisoft in titles such as For Honor, and this has evolved further with deep learning approaches emerging from Ubisoft's La Forge R&D unit, working alongside McGill University, as well as recent work from the University of Edinburgh here in the UK. In addition, there is other opportunities emerging for animation through use of deep learning, with some really great work again coming from La Forge in lip syncing systems. This would allow for facial animations to adapt to different languages and different scripts, and it doesn't require developers to go in and craft that by hand. This has already actually been deployed in commercial games with this particular lip sync technology used in the last Assassin's Creed game, AC Odyssey. Meanwhile, another complex problem for capturing player behaviour is in cheat detection. This is an incredibly difficult problem given that there are many subtle, bordering on indiscriminate ways that players can engage in a game and then avoid being detected, as they're using things like aim assist bots or wall hacks, or any other tools that can help them get an upper hand. CSGO, developed by Valve, has actually been slowly implementing numerous changes to their matchmaking processes and server authority. However, they actually started using deep neural networks as early as 2017. This allows them to identify bad actors by introducing a system called VACnet, a system that was built to integrate into the existing monitoring processes for CSGO called Overwatch, no relation to that other game, which actually recognizes potential bad behavior and then passes cheat reports to a human moderation team, and it's actually integrating into the same system that humans, actual CSGO players, can use to report other players. However, the big difference is the accuracy in submitted reports, where on average a human's report is only maybe accurate up to 30% at the time, whereas this system, VACnet, is actually achieving 80% accuracy on particular bad actors that it's spotting within the ecosystem. Meanwhile, at companies such as King, home of Candy Crush, there is an increasing focus on how to continue to generate new content for a hungry audience base. Hence, King have been working for some time now on a variety of deep learning tools and have a dedicated R&D unit for this. This ranges from automated playtesters to tools that support level designers and even entire level generation toolsets. Now, this is very much an ongoing and evolving platform with continued development behind it, and it's not entirely production ready. But it is evidence of the significant time and dedication required for ongoing platforms such as Candy Crush to integrate and utilise these technologies in a way that will help push further engagement. Now, the thing is, this is but a fraction of some of the innovations that are emerging, and sadly, I'm tight for time, otherwise I would discuss these not only in more detail, but also a lot of these other innovations that we're seeing on screen right now. But to quickly mention them, there are areas such as DLSS, which is deep learning supersampling. This is not only a process that can help replace anti-aliasing on graphics rendering, but it's also a means to achieve fast upscaling of graphics from 1080p over to 4K. We have the use of deep learning for texture upscaling, which is something that's actually becoming very big in hobby and modding communities. We have real-time text analysis to combat toxicity, which is actually a technology that has already been deployed in ecosystems such as Xbox Live. Automated testing for quality assurance, which I could actually dedicate an entire talk to, looking at different ways AI is being used right now for testing in games. And of course, things such as modulation or noise reduction in voice chat. And this is actually something that even recently the likes of Discord actually rolled out their own version of this into the latest versions of the client. And for all this DLSS, anybody who's running on a GeForce RTX GPU is able to capitalize on this technology. And it's worth mentioning, I didn't even mention anything in this presentation on player analytics, which is essentially data sciences employing very similar machine learning technologies in order to learn specific aspects of a player's behavior. There's a huge amount of growth in this space right now, and it is probably larger than it has ever been in the context of AI for video games. And that's really my critical takeaway for this presentation, is that hopefully you have a better understanding of different ways in which AI has been used historically, but also some of the big changes and why deep learning in particular is really catering to a lot of really unique problems that our existing AI technology has never really been able to support. And as a result, innovation in how and why AI is deployed in games is increasing at a rate that is beyond anything I've ever seen. But I think what's really interesting is that for the most part, it's not pushing innovation in areas we've historically employed it. We're seeing a paradigm shift. The idea of how AI can be used in games is changing quite drastically. And I genuinely don't believe that, for the most part, the idea of our existing mechanisms for non-player characters is going to change. We still want that authority and oversight. We still want the ability for programmers and designers to work together. But many of the subsystems and elements that surround these procedures and processes, these might actually begin to change and evolve. And as such, it's important as producers, designers, developers to be aware of these new opportunities, as well as the risks and challenges that each of them present. You may have noticed a recurring theme in this presentation that a lot of these deep learning innovations are being brought on by big names such as Valve, Microsoft, Nvidia, just to name a few, but there are a lot of other major tech companies right now investing billions upon billions of dollars into building these tools and systems to support their own projects and perhaps their partners and vendors. But that said, there is still opportunities for smaller scale projects and development outside of these larger companies, given how readily available a lot of the software and knowledge base is for getting started in deep learning. And so this has been something of a whirlwind I can appreciate in trying to get you up to speed on massive amount of work that's happening in this space right now. But I hope you found this insightful and also maybe actually learned a thing or two along the way. My contact details are at the bottom of the slide, as well as links to some of the ongoing work I'm involved in over at AI in Games, not just working with clients, but also the work that you actually see published on the YouTube channel. I'm more than happy to answer any questions or provide more detail on the topics raised throughout this video. But nonetheless, I really hope that you've enjoyed this talk and that you've gained something from it. Thanks for watching.